Good afternoon, grade 12s. This is Thursday, June 18th of 2020. Coronachem day 50. Day 50. And I've lost my marker. The question you got for homework related to a nomenclature was, what are the isomers of C5H10? It helps at this point to realize that I'm just checking for some glare, no glare, good. It is important to note that when you compare the formula of the molecule that you're asked to write the isomers of to the formula of its parent, meaning the molecule has the maximum amount of hydrogen that you could stick on to that number of carbon atoms, you can form a comparison where you see that there's two hydrogens missing. When two hydrogens are missing, it means there's at least a double bond or a ring, not both at the same time. Because to form that double bond, you have to use a pendant bond. So, pretend you have those hydrogen atoms. Take away those hydrogen atoms, those two will flip together to form another bond, because each one represents an electron, and the one electron from each gives you the two electrons necessary to form the bond. So compared to C5H12, the comparable saturated alkane, there's a difference of two hydrogen atoms. This indicates the presence of a double bond or a ring, but not both at the same time. If you have both at the same time, then you'd be missing 4 hydrogens. If you're missing 8 hydrogens, then you have 4 double bonds, or you might have a ring and 3 double bonds, or you might have 2 rings and 2 double bonds, and any combination that adds up to 4. For example, in benzene, you have 3 double bonds and a ring. So benzene, compared to C6H14, is missing 8 hydrogens. So the formula of benzene is C6H6. So that index of hydrogen deficiency is a good way of ballparking what your molecule looks like, or at least what features does it possess, which helps you then zero in on the possible isomers of that particular structure. So C5H10 has 10 isomers. They're all different molecules. They have exactly the same formula, but they're all completely different molecules, different melting points, different boiling points, different refractive indices, different densities, etc. So let's draw and name them. The first one, and the way to do this is to go about it systematically. Think of the biggest ring, for instance, so we can exhaust all the rings, but the biggest ring is going to have 5 carbons in a circle. Remember, there's only 2 hydrogens off each carbon, so you're going to use up 10 hydrogens to draw cyclopentane. Whenever you name a pentane that is cyclic, you put cyclo in front of it. This marker does not work well. I have to go and test all of them now because I put it down somewhere. So cyclopentane is the first possibility. And the next one is 1 carbon smaller. So it's cyclobutane, and you have 1 extra carbon atom to stick on there, so you're going to call it methyl cyclobutane. You don't have to really put the 1, because anywhere you put that methyl group is going to be the first position. So it's redundant to say 1 methyl cyclobutane. If you have the next smaller ring, and also obviously if you put it in a different place, that's 1, so there's no 2, because the place where you put it is 1 and there's no other ones to put. Now if you have a cyclopropane ring, now that leaves you with 2 carbons to play around with, so you can put them both on the same position. So that would be called 1,1, because that position is the first position. Wherever you put the substituents becomes the first position on the ring. So you have 1,1 dimethyl cyclopropane. The other possibility is you put it one at the first position, another one at the second position. That would be called 1,2 dimethyl cyclopropane. If you go to the third position, it's still 1,2, because then you would number it the other way. Then that exhausts all the possible ring isomers. Now let's go to isomers that contain a double bond. The first logical place to put a double bond is at the first position. That would be called pentene. You could put 1-pentene, but 1-pentene is redundant, because if you don't specify, then it's got to be at the first position. The second possibility, you put the double bond at the second position, that you would have to call 2-pentene. The metric system is now saying that you should call this if there's multiple substituents on the same molecule, they recommend you put the number as close as possible to the name. I think that's horrible. Pent-2-ene. I resist doing it for as long as possible, but sometimes it's good to know that you can resort to that if you're really stuck. But I would call that 2-pentene. The next possibility, oh, and by the way, when you have a double bond, it locks the molecule in that spot. The molecule is no longer floppy, it can't rotate. So you can either lock it with the two substituents in opposite direction. That would mean it's trans. I'll put a T for trans. If they're on the same side of the molecule, like they are here in number 7, you would call that cis-2-pentene. In the 8th possibility, what I've done is I can't move the double bond over here because that's still 2-pentene. So I've exhausted all the possibilities with a chain length of 5. So now let's move to a chain length of 4. 1, 2, 3, 4. If we numbered, it helps you to see the naming. The methyl group that's left over is put at the second position. If I put it here, we're back to a 5 carbon chain. So I put it at the second position. We're going to call that 2-methyl butene. Then I move it down the chain. This is the third position. So this is called 3-methyl butene. And then the last possibility is I put the double bond to the middle. So now it's 2-methyl. It's also got a methyl at the second position. So that would be called 2-methyl. Let's erase that 3 because it gets in the way. 2-methyl 2-butene. And here there's no cis-trans isomerism because if you flip it, it's still the same thing. Typically, if you do have 4 things attached and there's a double bond in the middle, then the 2 heavier ones will decide the cis-trans isomer. Wherever the 2 heavier things are, that's if they're on the same side, it's cis. If they're on opposite side, then you call it trans. Okay? Then that's it. That is all 10 isomers of C5H10. Now I'm going to continue with the notes related to organic chemistry. Well, there's the Brandon marker. Lost it momentarily. I'm just going to give you a hint. For the test tomorrow, I'm going to give you C6H12. All right? And you're going to have to name all the isomers of C6H12. The answer is in my playlist. So go find it. It's there. I did it years ago. Watch that. That's one of the questions on your test tomorrow. So I can't make it any easier than that. All right. Continuing the notes then. A little bit about organic chemistry. We left off at alcohols. Keep forgetting I'm blind. All right. Alcohols contain the hydroxyl group. They can be primary, secondary, or tertiary depending on how many carbon atoms are attached to the hydroxyl bearing carbon. Okay, so here's a primary alcohol. Here's the hydroxyl bearing carbon, and there's one carbon atom off it. This is a primary alcohol. Here's a propane molecule, but if you have an OH attached to the second carbon, that carbon which bears the hydroxyl has two carbons attached to it. That's a secondary alcohol. And here is another one, methyl propanol, but if I stick an OH on that second carbon, now there's three carbons attached to that hydroxyl bearing carbon. That's a tertiary alcohol. So primary, secondary, and a tertiary. Sometimes when they name alcohols, you'll see sec in the name or tert in the name. That's what it's implying. And this, by the way, is called 2-propanol. This is the official name for it. This is called 2-methyl 2-propanol. Okay, there's an all ending on an alcohol. Here's propanol on the second carbon, if you number it. So here's the longest chain. On the second carbon, there's a hydroxyl group and also a methyl group. So I say 2-methyl 2-propanol. A lot of times these little alcohols have their own little trivial names. This is called isopropanol. This is called tert-butanol because it's a tertiary alcohol. You could also call this sec-propanol, I'm guessing, although I've never heard it called that. How do you make methanol, which is the simplest alcohol? You can take carbon monoxide gas and hydrogenate it. It requires a high pressure, about 200 to 300 atmospheres, and high temperature, about 400 degrees Celsius. You can do that industrially. Carbon monoxide can be made by burning high quality anything, carbon, wood, but in a low oxygen environment, and then the carbon monoxide that results can be hydrogenated, but they usually probably use something like high quality coal or coke, and you get methanol from it. So preparation of methanol, that would probably be used in an industrial process. It's not something you would do in the lab. You can also prepare alcohols by fermentation of sucrose, which is table sugar. Most yeasts will do that. Yeast have a biochemical pathway that allows them to continue existing in the absence of oxygen. We have a similar pathway. When we don't have enough oxygen to carry on metabolism, we have an anaerobic pathway in metabolism, but what we do is we produce lactic acid in our muscles. So if you're exercising intensely and you can't get enough blood flow to the muscles to provide the oxygen, then your body switches to an alternate pathway and it starts to build. It still makes ATP so that the muscle can keep contracting, but you build up a byproduct called lactic acid, which eventually neutralizes the muscle so that you don't damage it. And then you will breathe more heavily for a while to pay back the oxygen debt. But what yeast does is their alternate pathway for making ATPs in the absence of oxygen is to produce ethanol as a byproduct, which is great for us because we like to drink ethanol. So if you ferment yeast, ferment sugar in the presence of yeast, you'll get ethanol, aqueous, and quite a bit of carbon dioxide gas. So this is prep of ethanol by fermentation. sometimes the fermentation process can be contaminated by side reactions. You can get things like methanol, which is deadly. If you drink it, your body turns methanol into formaldehyde, and we know formaldehyde is toxic. Sometimes certain fermentation processes, if they've been contaminated with things that don't produce ethanol, or by some side reactions by what organisms, I don't know, I don't understand the process fully, but you can end up getting methanol, and you don't want to drink methanol. But funnily enough, the antidote to methanol poisoning is a whole bunch of ethanol. So if you drink methanol, the antidote is to drink a whole bunch of ethanol so that it crowds out the methanol from your receptor sites, and it gives your kidneys time to excrete it before it poisons you. Here's a popular alcohol, which you don't normally think of as being an alcohol, but it is in fact. It's called cholesterol. So it's an alcohol because it ends in "ol," but it's also a steroid. Cholesterol is a steroid, and it's the steroid your body uses to make sex hormones. If you're male, well, actually both sex hormones are present in both sexes, but it's like 100 to 1 depending on which sex you are. There's cholesterol. So you find cholesterol in almost all your cells. It's absolutely necessary to life. It helps to make your cell membranes pliable, and then your body modifies it to make things like testosterone. Here's cholesterol then. There's the OH group that makes it into an alcohol, but it's also a steroid. And to be a steroid, you have to have these 4 rings locked together like that. And here's another steroid for your entertainment pleasure. You see, it looks very similar to cholesterol. It's got those 4 rings locked together. Except, you know, little changes make big effects. That's called, this is testosterone. So you see it's very similar in structure. If this ring becomes a benzene ring, then you get estrogen. So that's called aromatization. If you have a lot of testosterone in your body, it can sometimes happen that there's an enzyme in your body that causes this to become a benzene ring. Then you get too much estrogen in your body, and you can get side effects. It happens to young boys that the aromatization turns it into estrogen, and they can get female side effects like moderate breast development, but then it tends to go away. And in menopausal women, the opposite can happen. The estrogen can be turned into testosterone, so when their estrogen levels fall, they actually get a little bit of testosterone, and enough testosterone in their system, they start growing whiskers on their chin. It actually lowers their voice a little bit. It even changes their thinking slightly. So who knows why that happens? There must be some good biological reason for it, but it's very interesting to observe. Testosterone is a steroid as well, made from cholesterol in the body. So if you don't have enough cholesterol in your diet, your body won't make enough sex hormones, and it's going to cause problems. Okay. Another class of compounds is called the ethers. They can be synthesized by dehydration of alcohols. For example, if you take 2 ethanols and you put them in the presence of sulfuric acid, it'll dehydrate. Sulfuric acid is a powerful dehydrating agent. You will get the subtraction of water, and you'll form diethyl ether. It looks like a two-legged spider. So this is called dehydration, synthesis of ether. If you have a cyclic diol, or almost cyclic diol, so you could have a diol with hydroxyl groups on either end of it, okay? So here's the 4 carbons in it, and then there's an OH off the first and the 4th carbon, and if you put it in the presence of sulfuric acid, that same reaction will happen where you subtract the water molecule and you will create a ring ether. This is called tetrahydrofuran. We call it THF for short. It's a great solvent. It's an important industrial solvent. It's used, for example, in ABS tubing. If you have ABS tubing, which is the black tubing you use in plumbing, and the ABS stands for acrylonitrile butadiene styrene. So it's 3 monomers combined to make this plastic, which is excellent for plumbing. But you can melt it with tetrahydrofuran. This solvent is very strong for that plastic. You put some on there, the plastic literally melts off the surface. You can clean the surface of the plastic really well, and if you add enough of that solvent, you can actually melt the plastic pieces together. But they prefer to use actual glue, which fills the space. So you put a glue on there, probably has tetrahydrofuran as a solvent as well, and then you slip the pieces together, and they practically become welded together. You can't pull them apart. You'll break the tube before you can actually pull the weld apart on the plastic. All right, so the next thing is the carbonyl group. Carbonyl group is very useful synthetically for making all kinds of interesting things. Carbonyl group is anything with a C double bond O on it, and then you can have 2 R groups or less depending. It's found in aldehydes, ketones, carboxylic acids, and amides. Oxidation of alcohols can be used to produce them. Is used to produce aldehydes and ketones. So aldehydes have the basic structure like this. Ketones have the basic structure like that. For example, on page 1086 of your text, they show you cyclopentanol being oxidized. They don't specify what chemical they use. There are many chemicals available that can do oxidation. Some of them are mild at oxidizing, some are very strong oxidizers, so you have to pick them according to the fragility or the solidity of the molecule. And very often, if you have multiple other things going on, like a complex molecule, you might want to only oxidize one part of the molecule, so you'll pick your chemicals according to what will produce the most efficient effect. It's a vast science, and to do it well, you have to know a lot of things. So cyclopentanone and cyclopentanol. All right, so oxidation of cyclopentanol can give you cyclopentanone. Ketones also are important solvents. You can use the magic of pause there if you need more time to copy. Ketones are important solvents. Example, this we know as acetone. Carbon, 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 right? Carbonyl group in the middle, methyl group, that's acetone. The name for it, if you use IUPAC, is 2-propanone. They have an "one" ending if they're ketones. So prop because there's 3 carbons, and then there's a carbonyl group at the second position, so 2-propanone. If you have a slightly longer ketone, this is called 2-butane, so 1, 2, 3, 4. Carbonyl at the second position, so you call it 2-butanone. Sometimes you see butan-2-one. I hate putting the number in the middle of the word. That's the sort of official way to do it. I'm kind of old school. I still do it the old-fashioned way. Boiling point of propanone, of 2-propanone or acetone is 56 degrees Celsius. The boiling points are always important because very often you have mixtures that you want to isolate something that's in the solvent. So if the solvent is easy to evaporate, that makes it more convenient for use. 2-butanone has a boiling point of 80 degrees Celsius. And it's also known as methyl ethyl ketone. Sometimes they say ketone, and then they name the 2 groups that are attached on the side. So this is called the methyl group on this side, and this is called an ethyl group on that side. So you could call this methyl ethyl ketone. There's alternate naming systems, obviously. They also call it MEC for short. Let's move on to weak acids. So weak acids are the carboxylic acids. How are we doing for time here? I've got 13 pages of notes. I'm up to page 11. I might prolong the class a bit more than usual. Feel free to put me on fast forward. Sometimes the best way to watch videos is to put it on 1.5 times so you get through it quickly so you don't bore yourself. I think the limit is about 2 times faster than normal because then the speech patterns become distorted. So ketones are important as solvents. Whoops, sorry, copying the wrong thing. Carboxylic acid. They have the basic structure of C double bond O, the carbonyl with an O and an H. So it's like a hydroxyl group on a carbonyl. They're widely distributed in nature. They're found in many consumer products, and they can be made by the oxidation of alcohols. So take, for example, ethanol, and you oxidize it, you can produce things like, by partial oxidation, you can stop it to get acetaldehyde. But if you continue the oxidation, it turns into a carboxylic acid. So that's at a higher state of oxidation than the aldehyde. So you can add water to the aldehyde. That will cause more oxidation, and you get acetic acid. By the way, this is also called 2 carbons aldehyde, so it's called ethanal. You don't have to put a number on aldehydes, because the aldehyde group always has to be at the end of the molecule. So whatever you have in aldehyde, it's at the 1 position. And carboxylic acids to be made by stepwise oxidation of corresponding alcohols. You can also carbonylate methanol. So here's methanol, 1 carbon, then an OH. And if you add carbon monoxide using a catalyst, you will get acetic acid. And this is called the carbonylation of methanol. Page of notes. Esters. They're probably the most interesting substances. They have a carbonyl group with an oxygen and then another R group attached to that oxygen. And there's an R group on this side as well. So how do you make them? Let's take a simple carboxylic acid like acetic acid, the stuff we find in vinegar, and add ethanol to it. the two, when mixed, can condense to form an ester. And this would be called ethyl acetate. So the way you name esters is you name the part that's attached to that oxygen first, and then you name this bit by counting how many carbons it has. So acetate is, and you have to have an 8 ending on it. Okay, so acetate is 2 carbons. Actually, I should call this acetate is the trivial name. Ethan for ethanoic, right? Or ethane is 2 carbons. So there's 2 carbons here. So you call that ethanoate. So ethyl, ethanoate, ethyl, ethanoate. And you get water as a byproduct. This is called the condensation of alcohol plus acid to give ester. Sometimes they catalyze them with a little bit of acid, get a more rapid esterification. Esters are named by first by the alcohol, then the group from which the acid is derived. Esters have pleasant odors. Let me give you some examples. This is called pentyl acetate. 1, 2, 3, 4, 5. Yeah. Pentyl acetate. Smells like bananas. One, 2, 3, 4, 5, 6, 7, 8. This is octyl acetate, or ethanoid if you like, but everybody calls it acetate because it comes from acetic acid. So octyl acetate smells like citrus. Then you have ethyl. So you name the alcohol side first, the part that's attached to the oxygen. Ethyl, and this is called cinnamate because it probably resembles cinnamon. And guess what it smells like? It smells like cinnamon. One end. Cinnamon. Give you a few others. So the food industry has an arsenal of these substances available to add as flavoring to food. If you ever wonder why certain foods taste so strong, it's because they've had these things added to them. And I have a feeling that you give an animal any of these chemicals or any foods with those chemicals in them, typically they will reject it because their sense of smell is much more acute than ours, and to them it's probably an offense to their senses. It just overwhelms them. They don't like it, and it makes them turn away from the food. Very often animals will reject things that human beings love. It can also be related to the fact that, you know, if you give a cat something that contains sugar, I think most cats aren't interested in anything sugary. They might sniff at it for a second and they'll walk away. Ethyl pentanoate smells like apple. Propyl acetate smells like pear. You see, the molecules are all very similar in appearance, but each one has its characteristic smell, all of which is quite appetizing to most of us. So you can see why adding it to food creates the impression that you have a good food. They're not toxic because, I mean, the natural foods very often will have the same chemical. Propyl isobutyrate is rum. So if you want to make rum, you know, you can make cheap rum. You know how you do it? Take some water, add some ethanol to it, and throw some of this in there, and then stick a label on the bottle. that would be cheap rum. I don't know what the regulations are regarding alcohol manufacture. And probably you're not allowed to manufacture something as being, you're not allowed to misrepresent stuff, but I think the misrepresentation does take place. Sometimes the stuff you taste that passes for one type of drink makes you really wonder whether it wasn't just made by, you know, adding water, alcohol, and some flavoring agent. Fortunately, you can't really fake things like 12-year-old whiskey. Anybody who really understands what a good glass of whiskey tastes like are not going to be fooled by some cheap concoction. I think they've tried and they realized there's just hundreds of chemicals in the real thing that made it very hard to imitate or very expensive, so that it wouldn't be profitable. So you're better off just brewing the real thing. Raspberry. Here's what, this one's a pretty big one. 1, 2, 3, 4, 2. 4 peaks. And then the second one, Okay, this is called geranyl butyrate. And it smells like cherry. I say smell, it might taste like it too. Because very often what we perceive as taste is actually the result of our sense of smell being stimulated. I'm sure you've heard the rumor that if you eat an onion when you have a cold, you won't be able to tell the difference between an onion and an apple. Because when you can't smell the natural products that come off the thing you're eating, it greatly handicaps you in being able to taste it as well. I've always had a very good sense of smell, as all my students know, because I detest the smell of Doritos in class. And kids are always trying to sneak Doritos in, but I can catch them from a mile away because the smell is just like an assault to the senses. And I yell at my students when they bring Doritos into class because it distracts me from trying to teach. Maybe look up Doritos flavor, see what the chemical is that they use. So methyl phenylacetate smells like honey, and methyl salicylate is actually medicinal. It's called oil of wintergreen, and it's an ester, and it smells like wintergreen gum. It's a very appealing odor. It's very bracing. When you smell it, it smells good, and if you rub it on your skin, it's an analgesic like aspirin. I think it can lower your fever too. It might be, anti-inflammatory, analgesic, antipyretic. Don't quote me on the antipyretic part. But it's a dangerous thing though, because you don't want to take more than about 4 or 5 grams. If you take, even that might be too much, you might not want to go over 1 gram of the stuff. There have been emergencies where people have rubbed large amounts of methyl salicylate onto their skin. And of course it absorbs into your body. And when you poison yourself with salicylates, I don't know how easy it is to remedy. Apparently there's no way to counteract the poisoning. You get into, basically it stimulates you to start breathing really quickly, and you work yourself into a metabolic alkalosis, which is very dangerous. So I don't know if there are drugs that you can give to the person to, maybe you would have to counteract it with Diamox, the kind of medication they give to people who have altitude sickness. Don't quote me on that. If you take too many salicylates, go to the hospital. Last one. Propylhexanoate. Is blackberry flavor. This is oil of wintergreen. and it's also medicinal, interestingly enough. Okay, last page, folks. Or is it the second last page? No, second last page, but the second last page is kind of off topic. Esters can be hydrolyzed, meaning they can be broken down using water to yield an alcohol and an acid component. This reaction can be done with acid or base. So, for example, if you have methyl propanoate, 1, 2, 3. Here's methyl propanoate. Take methyl propanoate, add sodium hydroxide, any strong base will do, doesn't have to be sodium, it could be potassium hydroxide, and you will get sodium salt of propanoic acid, sodium propanoate. You get the conjugate base of propanoic acid with the sodium counterion, and you'll get methanol as your product. You can use this same reaction on animal fats to produce soap. That's called a saponification reaction. In a saponification reaction, in the old days, what they would do is they would collect the grease from cooking animal fat, like bacon, for example. You get a lot of oil melts and it collects in the pan. You can pour that oil out of the pan, add some strong base to it. In the old days, what they would do is they would add ashes from the fireplace, because ashes contain a lot of oxides of potassium and sodium from the wood that's been burned. And when you add water to oxides of sodium and sodium oxide and potassium oxide, you produce base. And then you let it stir over a fire. It would cause a saponification reaction. It would break down the fatty acids into glycerol, and it would break down the fatty acid esters into glycerol and fatty acids, which is soap. You can make laundry soap using bacon, for example. And basically, you've heard the word palmolive. What do you think that comes from? They use palm oil and olive oil to produce soap, and then what they do is they bleach it to get rid of any odors they don't want and any colors they don't want, and then they add some color to make the bar soap whatever color they might think is appealing, and then they add some esters that smell nice, so that when you put it on your body, you smell like perfume. So they add a little perfume after bleaching the product, so there's soap. But anybody can make soap because it's actually quite easy. You can look up saponification. The word for soap in French is savon, in Italian it's sapone, I think in Spanish it's jabón. Practice example on page 109. If you take propanol, which is an alcohol, and you combine it with propanoic acid, which is a carboxylic acid, in the presence of, usually they have a little bit of H plus catalyzed, but it can happen even without. You get the ester. And this would be called propyl, because there's 1, 2, 3 carbons there. Propanoate, because there's 3 carbons there. Propyl propanoate. And you can take any alcohol and any carboxylic acid and make the corresponding ester. The next thing is amines and amides. They are organic bases with 1, 2, or 3 groups attached to nitrogen. So here's a couple examples. Ethylamine. You can have diethylamine. You can even have, notice the number of hydrogens decreases as the number of alkyl groups increases. You can even have triethylamine. And you can even have 4 attached on there. Of course, then you get ammonium-like behavior. And so you'll have a counter ion like, say, chloride. This would be ammonium. This would be called tetraethyl ammonium chloride, whatever the counter ion happens to be in that case. Very often these are used for disinfectants. If you have long chains on there, they actually disrupt cell membrane. So whenever you have a disinfectant cleaner, it's an ammonium compound very often. Amide linkages from protein form protein by dehydration synthesis of amino acids. I'm going to show you. What that looks like. I'll try to connect two simple amino acids. Glycine is the most simple amino acid. Okay, in biochemistry, if you want to draw an amino acid, it's always like this. You have a hydrogen connected to a carbon, then the simplest one is another hydrogen, that's called glycine, and then on one side you're going to have a nitrogen group, and on the other side you have a carbonyl group with a carboxylic acid. So this would be glycine. If you take 2 glycines and put them next to each other, what happens is, now I forget which one loses what. I think what happens is the nitrogen ends up attacking the carbonyl, and then in the process, one hydrogen is lost from the nitrogen and the OH is lost from the carbonyl. So in the end, what you get is H2N C. There's the H over there, still there. Carbonyl now is like this, but now it's connected to the nitrogen that was this one, and there's still one hydrogen left on the nitrogen, and then there's the next carbon with the hydrogen on it, and then the other side has the carboxylic acid. So now if you connect 2 glycines and you subtract water, you get a dehydration synthesis, and you get a glycine. You get 2 amino acids stuck together. So your body does that with amino acids to stick them together to form proteins. Now, one last thing I want to mention, because it's a whole course in university. This one little idea is actually it's more than one whole course, but I'd be remiss if I didn't mention it. Some molecules possess non-superimposable mirror images. Of themselves among their isomers. So any compound containing carbon atoms with 4 different attached groups are chiral. What does that word mean? It means that you can make them look like mirror images. Let me show you what a mirror image looks like. Left hand and right hand are mirror images. Okay? They look as if you take your left hand and put it in front of a mirror, the reflection is going to look like a right hand. They're mirror images, but they're not superimposable. See, the thumbs end up on the wrong side. Okay? So if you put a left hand glove on your left hand, you can put it on your left hand. The only way you can put a left hand glove on your right hand is if you turn it inside out. Because your hands are non-superimposable mirror images. Molecules also possess that property. They have identical chemical properties, except when they encounter a surface that has an asymmetrical properties, like say a protein. For example, if you take morphine can plug into a special receptor in your body, and it produces a whole host of effects, among which is even euphoria. So it's quite addictive. chemists have found that you can take a molecule that looks very much like morphine, but you flip one of the carbons so that one of the groups is pointing the other way. It now becomes a molecule that resembles morphine, but does not elicit the same effects. In fact, dextromethorphan is an opiate. It's a substance that looks like morphine, but it doesn't elicit all the same highs as morphine, although it's a great cough suppressant. So that's what they use it for. Here's an example of a chiral molecule. I'll just draw you one example. I'm not going to test you on this part, because don't worry, you'll get enough of it in university anyway. Organic chemistry 2. Example of there's a special name for it, a non-superimposable mirror image is called an enantiomer. So a molecule with carbon with 4 different things attached to it. These molecules look identical because they're mirror images, but they're actually chiral. And on top of that, molecules that have this property, if you put a certain type of light through them, it's called plane polarized light, one molecule will rotate at 20 degrees clockwise, the other molecule will rotate at 20 degrees counterclockwise. And what happens when you have a mix of these two equal amounts, one rotates it this way, the other rotates that way, they cancel each other out. So you get a mixture that's dextrorotary and level rotary. I'm not saying that this one is dextrorotary or level, I'm just saying for the sake of argument. When you have a mixture of them two together, they call it DL, and then they'll say the name of the molecule. So an example of a molecule that has that capacity is, for example, amphetamine. You can buy amphetamine DL, which has the dextrorotary and the level rotary isomers. One is called benzedrine, and the other one is called dexedrine. Dexedrine used to be used as a diet pill. Benzedrine is an upper. It'll make you very high, and it'll agitate you if you take enough of it. The mixture of those two drugs is DL amphetamine. Guess what they use that for? You ever heard of something called Ritalin? Same thing. They just put a different name on it. Ritalin is DL amphetamine. So, yeah, it's paradoxically it calms kids down. If you're what they call have attention deficit, so as they call it, which I think is a fake disease, because basically young boys, what they want to do is run around and make a lot of noise. That's totally normal behavior. There's nothing wrong with that. Too bad for teachers who would like to have the kids sit still and not do anything. If you have little kids who are 7 years old and are a little bit hyperactive, welcome to the real world. That's what little boys do. They need somebody to give them something to do. Anyway, when you give them amphetamine, they calm down because their brain is crackling with activity. They're high. That's why I have a problem with it. Anyway, pure samples of one or the other enantiomer rotate plane polarized light in opposite directions, like I said earlier. A solution of both enantiomers does not exhibit optical activity because the enantiomers oppose each other's action, and it is called a racemic mixture. Many important drugs are racemic, with only one enantiomer being active. Example, amphetamine has 2 isomers. Benzedrine is a stimulant. Dexedrine is merely a diet suppressant. And when you mix the two together, they use it for calming down hyperactive kids. And that is it, folks. That's the whole course. Tomorrow I will have a test for you in the morning, and it'll be due 6 p.m. That's the last test you're going to do with me. And by Monday I should have some marks. Tuesday the marks are due, so don't bother me till then. I'll have it done for you, okay? And I'll see you tomorrow.